Worked problems for chapter 6. I want to go ahead and give the credits. So some of the problems are taken from Brown and LeMay's chemistry, some from Zumdahl's chemistry. Some of the multiple choices are taken from Mr. Mack's AP chemistry site. And maybe occasionally there will be a problem from McMurray and Fay's chemistry. Answers are provided by myself. So let's go to the next slide. Next. So the first problem is just a kind of a review, actually. So a review of the different subshells. And so we said that for the S subshell, it's spherical. And so each row or period in the chart will have one S subshell, which can contain 2 electrons total, max. Then the associated L angular momentum number, the second quantum number for that, is 0. So whenever you have an S subshell, it's associated with the number 0. So when we say 1s, which is the way we usually describe it, if you were going to write that 1s in terms of the 2 quantum numbers, you would write it as 1, 0. Next slide. So this is the way that it would look. It's a spherical shape around the nucleus. If you had a 2s, it would be a sphere, but it would just be a larger sphere, and it would encompass the first one, and there would be what's called a node, N-O-D-E, around between the first one and the second one, where there is no electron density. Next slide. The p orbitals or suborbitals are shaped like dumbbells, basically. I mean, are kind of like in extreme case of a peanut, which starts with P. That's why I say that. Really, they don't look very much like peanuts, but a little bit. They really look like dumbbells, and there are 3 of them, and they're oriented in the X, Y, and Z directions. So usually you could call them PX, PY, PZ, but to put a number on it, the number would be like, for example, you could call one of them -1, one of them 0, and one of them +1. And that would just be so that you can say there's a number for that. So 4 quantum numbers. So the first quantum number is the N number, which is the main shell. So that's going to be like 1, 2, 3, 4, 5. And then the second quantum number is the angular momentum or azimuth number, which is going to be for either for S, P, D, or F suborbitals. So they associate the numbers 0, 1, 2, and 3 with those. Next slide. So here's another picture of your, this is, okay, so this is the D subshells. So there are 5 of these, and they are not along the axes for the most part, except for the last 2. So there's D, Y, Z, D, X, Z, and so forth. Each of these can contain 2 electrons, and be careful here because notice that there are 4 lobes, so it might appear to you that each of these could hold 4 electrons, but they can't. Each orbital, no matter what it is, can only hold 2. So D would be associated with something that's in N equals 3 or higher, but you cannot have D's if you're in main level 1 or 2. You have to be at least at 3, otherwise there's not enough room for these to exist. And they're also associated with, so S is 0, P is 1, so D would be 2. Okay, so the L number for D electrons, or sorry, for D subshell would be 2. Next slide. All right, so find a frequency from a wavelength and vice versa. We're going to use the same formula for both. The speed of light, c, equals the wavelength lambda times nu, which is the frequency, and they have to be in the right units. So the wavelength has to be in meters, the frequency has to be in seconds to the -1, or hertz. So when you see hertz on like your radio dial, if it's AM, it's going to be in kilohertz or thousands. It's going to go from about 550 up to about 16 to 1700. And if you go to the right of that, then you go in. So the AM dial is actually called medium wave. If you're dealing with ham radio or radio in general, it's called medium wave. And then when you go past that, you get into the high frequencies that are used in some of the short waves. Some of the shortwave bands are in, actually quite a few of them are in the HF range from 3 to 30 megahertz. So that would actually be above the AM dial in frequency. Anyway, that has nothing to do with our problem. So if we're trying to find the frequency, we would divide both sides of this equation by the wavelength. So we would divide 3 times 10 to the 8th by the wavelength. Okay, on the right-hand side, the lambdas are going to cancel, and we're just going to have the nu left here, that thing that looks like a V. This thing right here is actually the Greek letter nu, or N, not V. So anyway, it would be the speed of light, which is 3 times 10 to the 8th meters per second. Then they're telling us the wavelength, so divide 3e8 by 3.56 e minus 11, and that's going to give you 8 plus, it's going to be about 10 to the 19th, and I can't go to the answer yet. Actually, I think it'll be 0.5 times 10 to the 19th, which would be 5 times 10 to the 18th, approximately, which would be in hertz. So 1 hertz would be 1 cycle per second. A kilohertz would be 1,000, and a megahertz would be 1,000,000. So your FM dial goes from about 88 to 108 megahertz. So that's millions of hertz. So that's obviously a way higher frequency. So let's see, 88 to 108 is going to be between 30 and 300. So that's going to be in the VH, let's see, 3 to 30, 30 to 300 would be in the VHF range, where most of your main TV stations would be in that range also. So like for everything, I think from channel 2 up to 13 or whatever, would be VHF. And then if you go above that, when you're above, let's see, so 3 to 30, 30 to 3,000. So when, no, 3 to 30, 30 to 300 megahertz. So 300 and above megahertz. 300 and above to 3,000 is called UHF, which some of the TV stations end up being in that range anyway. All right, here, what I would do if I were you is to do these problems, I would immediately convert this to hertz. So, I mean, I will just go ahead and take a moment to do that. So it would be 102, let's see, it would be 102 million, let's put a comma here, 500,000 hertz. And again, I have no problem writing this stuff out. It's just that with this particular marker that they provide you with here, it's very tedious. And plus, even after I go through all the trouble to do it, you can't read it. So it's 102,500,000 hertz. And so I would immediately convert it to that before I started to do the problem. Use the same equation we used up here, C equals lambda nu. In this case, we're given the nu, so we divide both sides by nu. And we get that lambda is C over nu. In other words, it's 3 times 10 to the 8th divided by this number right here. And this number right here, so 3 times 10 to the 8th divided by what is going to wind up being 3, 6, 7, 8. So it's going to be divided by 1.025 times 10 to the 8th. So it's going to be roughly 3 meters. So let's go to the next slide. So down here, we see that the answer was about 3 meters. It's actually 2.93. If you consider a meter to be about 3 feet, that's about 9 feet, which is maybe the length of some small cars. So in other words, this FM station at 102.5 has a wavelength about the same length as certain smaller cars. Well, I don't know if there's any cars that are that short, but maybe some of the hybrids or whatever. And then up at the top here, we did get 10 to the 18th hertz. So anyway, so out of all the things we're going to do in this chapter, this is going to be one of the more important ones. So you'll want to remember this, really, just memorize it, because it's just something that'll be useful to you for the rest of your life, probably if you stay in any kind of science. But it'll be on the formula sheet too. So, I mean, if you can't remember it, you can always look it up, but I'd recommend you just memorize it. So the wavelength times the frequency of anything in the electromagnetic spectrum will equal the speed of light, right? Now, sound is not going to be in that category because sound doesn't travel at the speed of light. I forget the exact speed it does travel at, but it's much, much slower because sound doesn't travel through what used to be, and maybe still should be referred to as the, oh gosh, I can't remember the name they used. I'll probably think of it in a minute, but anyway, they used to think that there was an ether is what I'm trying to think of. And this is not the same thing as the ethers you talk about in organic chemistry. And I still think that that's probably correct. There has to be something that waves travel through. And so, I mean, they did Michelson, Morley, and I don't want to get into that. I have my own thoughts about that experiment because it seemed to prove that there was an ether, but they didn't like that idea, so they kind of changed things up to suit the way they thought things should be for various philosophical reasons that go beyond chemistry or physics or anything like that. So I happen to believe that there is an ether, and that I mean there are several experiments that have demonstrated the presence of this ether. But anyway, sound goes through a different medium. It goes through air, so it can't go as fast. So let's move on to the next problem. For this one, we are going to figure out what the energy is, and we have to use a different formula. And that is that the energy is Planck's constant, which is 6.62 times 10 to the minus 34th joules per second, joules times second, sorry. And I'm writing it out. Okay, so forget that. I was writing Planck's constant, but so it's H, which is Planck's constant. So H is an abbreviation for Planck's constant times the frequency. So we see here that the frequency and the energy are related. They're directly proportional. In other words, if you increase the frequency, you're increasing the energy, and you'll want to remember that, okay? So if the frequency is this number right here, and it's in the right units already, it's in 1/2 or second to the minus 1, I can't get this thing to work right. That goes right there, and then you just put in what the value for H is, which is 6.62 e minus 34 joules times second. And I need to mark that out better so you won't think that's supposed to be there, because it's not. And just multiply those. So multiply 6.62 times 10 to the minus 34th times the number that you have for frequency, which is 24, times 10 to the 20th, which would be 2 times 10 to the minus, 2 times 10 to the 19th. Let's go to the next slide. So actually it's 3 times 10 to the minus 19th. So multiply Planck's constant, which is here, times the frequency, which they gave you in the problem statement. When you multiply these exponents, you add. So minus 34 plus 14 is 20. So 7 times 4 is actually 28. And that, so it would be about 28. Well, actually, it's about 7 times 5, so it's about 30 times 10 to the 20th power, minus 20, sorry. So, but if you change the 30 to a 3, you're making it smaller, so you have to make the exponent bigger. So that would translate to 3 times 10 to the minus 19th joules. Or, I mean, if you're doing it on a calculator, you don't have to worry about it anyway. But what I typically do is I try to do a ballpark figure in my mind just to make sure that the answer is reasonable. All right, so anyway, this is going to be your second main equation. And again, they're going to be in the formula sheet, but if I were you, I would just memorize them because they're useful. Excuse me. So this is E equals H nu, and this is going to be like the second main thing that you'll want to remember for this part of this chapter. Next slide. Okay, so what is the longest wavelength line? So just very briefly, we talked about this in some detail in our lecture notes, but like if that line I just drew is n equals 1, and then the next line I'm going to draw, we're going to say is n equals 2, and then it would be 3, 4, and 5, and so forth. Then, okay, let's look at this for a minute. Longest wavelength means shortest or smallest frequency. Because the longer the wavelength is, the shorter the frequency is. And the reason is because for all the different points on the electromagnetic spectrum, when you multiply frequency times wavelength, you have to get the same number. And that number is the speed of light. So if you make the wavelength longer in meters, then you have to make the frequency shorter or smaller. So longest wavelength line would be the shortest frequency. And remember, the frequencies and energies are related directly. So that means also the smallest energy. So in other words, what this is saying is that we want the energy change to be the smallest. And that would happen when you're only falling down from one level to the next lower level, like what I just drew there. Now for infrared light, that's going to be produced when we fall down to n equals 3. N equals 2 would be visible, n equals 1 is ultraviolet. So we want this to fall from 4 to 3. And that's mentioned here, but you can also figure it out just in your head without doing too much thinking. So let's go to the next slide. So we want this to fall from 4 to 3. So we're going to write the 4 over here on the right. So 1 over 4 squared, and then it's going to be subtracted from 1 over 3 squared here. So in other words, it's going to be 1 over 9 minus 1 over 16. So I would just do that first. I mean, just take your calculator and subtract 1/9 minus 1/16. Multiply it then by your r, which is your Rydberg constant, which will be given to you, and it's also on this slide right here. 1.1 times 10 to the minus second nanometers to the minus 1. Multiply that times whatever you get over here, which turns out to be 0.0486. So multiply this times this, and that's going to give you 1 over the wavelength. But you need the wavelength, so you have to take the reciprocal of whatever you got there to get the actual wavelength. And when you do that, you get 1876 nanometers, 1876 nanometers. So clearly that's not in the visible range, right? Because we said what for the visible range? And you might want to remember this also. It's about 400 to 750 nanometers. And so this is clearly a longer wavelength or shorter frequency than visible light. So that puts it in the infrared range. Next slide. All right, use this diagram to do the filling of atomic orbitals. So what we're going to do is we're going to start on the energy scale on the left and go up. And we'll just name these as we go. So we want to start at the bottom and go to the top. So it's going to be 1s, 2s, 2p, no surprises here. And then we'll keep going 3s, 3p. Now we're going to have to stop because look, before we get to 3d, notice that 4s, this is what's causing kind of like the problem. It's not a problem, but it's causing the mess up here, the difference. And that is because this 4s is lower in energy. And we know these are going to fill by their energies. They're going to fill a lower energy orbital first before they go up to the next higher one. Just again, to use the roulette wheel example, when you throw a ball into a spinning roulette wheel, it'll eventually fall down to the lowest accessible space available to it, which is going to be down at the bottom in one of the slots for one of the numbers. So here we're going to hit the 4s level before we hit the 3d, but that's kind of like cockeyed, right? And it isn't what we would have anticipated, but that is the way it actually happens in real life. And again, I talked about this quite a bit in the lecture notes. That's why we see the 3D, the whole 3D row here, move down one row in the chart below where it theoretically would seem to be. So it's moved from the third row of the chart down to the fourth row so that it can come after the 4s's here. So the 4s's, the first two elements in the fourth row will fill first, and then the 3D. So in the chart, like if let me just real quickly sketch the chart. So I mean, this is a really bad approximation of what the chart would look like. So we have two rows here. Actually, let's see. So 1, 2, 3. So actually we have 3, right? Is that right? And then when we get to the fourth row, so 1, 2, 3, and then when we get to the fourth row here, we would fill the 4s's, and then that would be these first two elements here. And then after that, we would do the 3Ds. But they're in the fourth row. So all of these are 3Ds here. Oh, this thing is just not working today. Not that it ever does particularly. So here are the 3Ds. But they're in the fourth row, okay? So that's what's happening. So that's why the chart's like this. So again, I said this several times in the lecture notes, but the third row here should, I mean, we would anticipate that the 3Ds should be here, but they're not. So let me put a parenthesis around this because they're not here. We have to move them down where they actually are in terms of the way the atoms fill. So we put them down here in the fourth row. Okay, so next, and here are the answers. So next, this shell, in other words, the N number and then the L number. So this one is the N number. That's the first quantum number. And this is the L. That's not a 1, it's an L. That's the subshell, and that's the second quantum number. And if we have a 4, well, I mean, they're telling us, so N is 4. So it's the fourth shell, and the L here the number is 3. So remember, the way they go is S, P, D, and F. It just takes forever to do this. S, P, D, and F. So those are the subshells that we'll actually talk about in this class. So as we said before in the lecture notes, S is associated with the number 0, just so we can assign a number to it, so that we can say at the end of the day that we have 4 numbers that we're assigning to each electron. And so they just go 0, 1, 2, 3, just like that. So the only trick is you have to remember that they start at 0, not 1. So anyway, if it's 3, then that means it's F, so that means this is 4F. And that's all we're doing here. So, I mean, that's pretty easy. Next slide. And here's your answer. Okay, next slide. Now they want us to do orbital notations for the electrons and the orbitals for the following quantum numbers. So let's do these one at a time. All right, so N is 2, so this is going to be 2 something, and L is 1, so that's P. And again, I guess I could rewrite this, but so S, P, D, F, let's just rewrite it because the more you see it, the more you'll tend to remember it. That is, if you can read my writing. S, P, D, F are the 4 suborbitals that we actually have to worry about. So the numbers associated with those, that's supposed to be a P, for goodness sakes, are 0, 1, 2, and 3. Okay. So what we have ourselves here is a 2. So just look back up at the stuff I wrote at the top and see what letter is associated with that. And then we also know that N is 4. So this B is going to be 4, and then it's going to be D. And that's all we're doing here. So I'll let you guys, because there's not that much here. Let's just finish it. So this one is going to be 3 what? Well, it's the same thing, right? It's L equals 2, so it's going to be 3D. Next slide. Next slide. Give the allowed combinations quantum numbers. So for A, it would be 3S here would be, and I'm not going to do it this time where I'm going to rewrite all these out, but it would be SPDF and 0, 1, 2, 3. And so the number here would be 3, and why don't we write it as a set mathematically? So S is 0, and so that means that the third number here, and they're actually only asking for the first 3, not the fourth spin number. So the first one would be 3 because it's in the third row. Sorry, yeah, okay. The third, it's the third orbital, and then S is always 0 because it's SPDF is 0, 1, 2, 3. And then when you have a 0 magnetic number, when you have a 0 azimuthal number, the magnetic number has to be 0 because it's anything between 0 and 0, but there's only one thing between 0 and 0, and that's 0. And if you didn't get that, wait till we do the next one, maybe that'll help clear it up. So for part B, the N number is 2, and the N number is just going to be the number that you see. But for P, do you remember SPDF is 0, 1, 2, 3, so P is 1, and that means that the M sub L here, the magnetic number, could be anything between plus and minus 1. Because P's, there are 3 of them, so we just arbitrarily say that one of the P's is minus 1, 1 is 0, and 1 is plus 1. So this third number here could be 3 different possibilities. And I'm not sure exactly how to do that, but so it could be either minus 1 or 0. So let's make another kind of like set inside this set here and say this one could either be minus 1 or it could be 0 or it could be plus 1. And I'll actually go ahead and write plus 1 just to make it clear. And then we'll close the original set. And again, I apologize for this really bad writing, but it's hard to do with this thing. So it would be 2 and 1, and then it could either be minus 1, 0, or plus 1 for the magnetic number. So this is going to be your M sub L, or your magnetic number here, M sub L. So this is your main number N, and then this is your L subshell number, and then this is your M sub L. And then if you wanted to have the whole set of quantum numbers, you'd have to have the fourth number over here, which would be your electronic spin. That's either going to be plus 1/2 or minus 1/2. but we don't need that here. And then for this one, okay, it's going to be 4. That's the N number. And then it's SPD, so 0, 1, 2. So it's 2 for your L number. So this is your L number. This is your N number. And then your M sub L can be anything from plus to minus 2. So there's 5 different possibilities there. So I'm not even going to write those out. I'm just going to put like a bracket here and then close it. And in that bracket, you would write everything between plus 2 and minus 2. In other words, you would write plus 2, plus 1, 0, minus 1, and minus 2. Okay, so there's your answers. Next slide. Next slide. This is just to review what we said in the lecture notes. These first 2 columns or groups represent the filling of the s suborbitals. The last 6 over here represent the filling of the 6p suborbital available slots. And again, just to review, there's one orbital here for the s's. That's the spherical thing. So it can take an up electron and a down electron. So this first column represents when you're putting in the up, or we can think of it that way. And then the second column is when we put in the down. And then the same thing over here, except it fills by Hund's rule. So this would be spin up. Carbon would have 2 spin ups. Nitrogen would have 3 spin ups. So you'd have all 3 of your p orbitals half full at nitrogen. And then when you get to oxygen, you would start putting in the spin downs. So you spin the 1 spin down, 2 spin downs, and the neon would be all 6 electrons in there. So neon would be, for example, spin up, spin down, spin up, spin down, spin up, spin down. All 3 of the orbitals would be full, and each would have 1 spin up and 1 spin down. And then for D, it would be the same thing, except that you have 5 orbitals. So you would have 5 orbitals with 2 electrons in each orbital, so that's 10 total. So the way they would fill would be to go spin up, and then the second orbital spin up, the third orbital spin up, 4th spin up, 5th spin up, and then start here, go back to the first one, spin down, spin down, spin down, spin down, and spin down. So this area here is called the transition metals. We don't talk about this very much. We talk about it some. And also, if you go to grad school in chemistry, you don't really talk about these that much unless you take the specialization that's referred to as inorganic chemistry, where that's what they mainly do study, is the transition metals, which they're actually quite fascinating. And then the F suborbitals would be filled from right there to where I'm drawing this line over to here. So that's 14 columns because there are 7 suborbitals. Next, write the atomic configurations for these things. So O, atomic number 8, means it has 8 electrons, is going to be, and I'm going to just do this from memory, 1s2, and then I'm going to stop here after O and let you guys do the other 2 as an exercise. You just do them the same way I'm doing these. And then it's going to be BCNO, so it's going to be 2p4. Yeah. So, I mean, oxygen would be what I just wrote. So if you look at the chart, which obviously I can't access right now, your 1s1 would be hydrogen, 1s2 would be helium, 2s1 would be lithium, 2s2 would be beryllium, and then 2p1 would be boron, 2p2 would be carbon, 2p3 would be nitrogen, and 2p4 would be oxygen. Fluorine would be 2p5, and then neon would be 2p6. And then you would go to the next row, which actually I think that is sodium. I mean, it's not like I have the whole chart memorized, but I do have part of it memorized. So for sodium, you would have everything that we have here, except that the 2p would be 2p6. So you'd have 1s2, 2s2, 2p6, and then you would come down to the next row, and you would have 3s1, right? Yeah. Let me just make sure that's right. Before I go on to the next slide, let me just double check this. So 2, 4, yeah, so that's right. So sodium, you would come back to the third row, all the way to the far left of the chart, to the third row. There's sodium. So its configuration would be 1s2, 2s2, 2p6. 2p6 would be for neon, and then the next element over would be in the third row. So come down and over to the third row to sodium, and then you're back in the s ring. So you add 1 electron to the 3s suborbital, and so that's 3s1. Now remember, we said there was another way we could do that. So like for sodium here, instead of writing it that way, you could just write a bracket and put neon in here. Ends are kind of hard to do. And then write just the 3s1 part here. So just 3s1. Excuse me. And that means the same thing as what we wrote up above. And this line right here is supposed to represent 1s2, 2s2, which I just didn't want to write it all over again. So do this one too. So you just come over to 3 more. So, I mean, I'll just tell you it'd be 1s2, 2s2, 2p6, 3s2, and then I think it's going to be 3p2, yeah. But you should write that out as an exercise. Okay, next slide. And anyway, the answers are here. Next slide. Ham radio operators, which I am, often broadcast on the 6-meter band. Well, that's actually wrong because sunspot activity really is low right now. And it's ham radio depends to some extent on sunspot activity, at least it's some bands. And this is one of the ones that does, 6 and 10 meter. And so right now, the 6-meter band is just about dead. I mean, it's not that you couldn't use it, it's just that there aren't that many people that are using it right now, which is unfortunate. And while we're on the topic here, and since I'm not really pressed for time as much in this particular set of problems, because these are not particularly difficult, while we're on the topic of sun activity, no, we've been hearing for years that the Earth is going to warm and the ice caps are going to melt and we're going to see floods in Miami. Well, first of all, even if the ice all melted in Antarctica and in the Arctic region, nothing's going to flood because the water level won't rise because ice melts. And then secondly, what they're saying now, scientists are saying now that the sunspot activity is going to stay low for the next maybe a decade. And what that means is that we're going to cool. Not that we ever really heated up that much in the first place. And I mean, I would question, like a lot of people would, a lot of scientists would question the so-called math and science that went into these studies in the first place. I think it's more, I mean, maybe I better watch what I say because this is going on YouTube, so maybe I better kind of quit at this point. But anyway, if what these scientists are saying is true, then we're going to see a decrease in temperatures, not an increase. So, I mean, even if there has been an increase, we certainly haven't seen any dramatic effects as they predicted. I mean, we haven't seen any effects, really. I mean, nothing has changed. And now they're saying, now the same scientists are saying it's going to cool off for like the next decade. And in fact, they're even saying we may go into an ice age. So if you're giving your money to a certain individual or you're paying carbon taxes, you may as well forget it. Hopefully I won't get this video pulled for saying that. All right. And then anyway, we're going to do this one the same way we did the ones at the beginning of this section. It's just C equals lambda nu, and I'm not going to write it again. So what you'll do is you'll just say that lambda is going to be 6 meters. C is 3 times 10 to the 8th. Divide 3 times 10 to the 8th by 6. Which is going to be a half times 10 to the 8th, which is 3 times 10 to the 7th, which is 30 million, so it would be 30 megahertz. Anyway, what you'll do is you'll divide 3 times 10 to the 8th by 6. Let's just do that. So that's going to be I'm going to do it in my head. It's 0.5 times 10 to the 8th, which would be 5 times 10 to the 7th, which would be 50 megahertz. So at the end of this problem, once you figure out your answer, it's going to be in hertz, but they want it in megahertz. So to convert it to megahertz, you just divide by 10 to the 6, or just multiply by, it would be 1 megahertz over 1 million hertz. Either way, you're going to get the same answer. It's going to be A. So just use C equals lambda nu. Now for this number 11 down here at the bottom, we're going to have to use both of our formulas. So first of all, let's start with the fact that it has an energy of a certain number of joules here. So I probably won't even try to do this in my head because it's a little too complicated. But first of all, we're going to use equals h nu. And we're going to convert the energy here from joules to the frequency in hertz. So the energy here, so actually let's rewrite this. So it's going to be nu equals E over h, where h is Planck's constant. And then we'll just substitute in. So Planck's constant h is 6.62 E minus 34, and that's going to be in joules per second. I keep saying joules. It's joules times second. The reason I keep saying that is because I'm trying to write and talk at the same time. So that would go here. And then the energy was given in the problem statement here. So just substitute in that number right there for the E and 6.62 E minus 34 for H and divide it. And that's going to give you a number which is going to be your frequency. And it's going to be in the units you want it to be in, which is in hertz, Hz, or cycles per second. Now take that number and bring it over here and put it in that other equation, which was C equals lambda nu. So the nu is going to be the number that you just got when you did that division. C equals lambda nu. And of course we know what C is, right? C is the speed of light, right? So this is actually pointing in the wrong place, so it should be pointing right there. Okay, so here we know nu now because we figured it out up here in part 1. And we know what C is, so we can, again, just divide both sides of this equation by nu. And over on the right-hand side here, the nu's are going to cancel. And you're going to have lambda C over nu, which you can now put the nu value that you figured out up here over here, and put 3.8 on N for C, and that will give you your wavelength. So let's go to the next slide and see what the answer was. And it turns out that it was 3.79 times 10 to the minus 7th, so it was E. So just be sure that you can get the same answer by doing this yourself, okay? Don't take the chance, don't walk into the test and expect that you're going to be able to do it just because you watched when I did it, because it doesn't usually work that way. And then up here at the top, we did get what I said. We got 50 times 10 to the 6th hertz, but they wanted it in megahertz. That's why I had to change it. So to do that, you have to divide by 1 million. So just use your conversion factor. Your conversion factor here would be that 1 megahertz, which is the capital M hertz, the capital M Hz. So 1 million would be 1 megahertz. 1 million hertz would be 1 megahertz. Or just remember that mega, capital M, stands for 1 million. Okay, let's go to the next slide. All right, number 12 at the top, of the following transitions, which will result in the emission of the highest energy? Okay, so remember, like, here's your nucleus, and then let's say this is n equals 1, and then n equals 2, and so forth. The one that's going to result in the emission of, so let's stop there. If we want it to be an emission, we're going to have to start above and drop down. That will emit a photon of light. If we go from down up, like if we went from 1 to 2, we'd have to absorb energy for that to happen. So first of all, it's going to have to be something going in the down direction. So A could be right. B couldn't be right because it's going in the wrong direction. So is C. And so is E, it looks like, yeah. So that already eliminated 3 of them. So it either has to be what, A or D, right? It has to either be 6 to 1 or 6 to 3. And then the next thing we need to look at is it's the highest energy photon is going to come from the most drastic drop. In other words, the one that drops the furthest is going to produce the highest energy because it's dropping from a higher to a lower energy. So the net energy released will be higher for a larger or longer drop. So that would be A. So the answer here is going to be A, because going from 6 all the way down to 1 is more of a drop than dropping just down from 6 to 3. Number 13, the lines in the emission spectrum of hydrogen result from, and I'm just going to go ahead and give you the answer. It's going to be D, energy that is given off in the form of visible light when an electron moves from a higher energy state to a lower energy state. Okay, let's go to the next slide. Oh, and these are the answers. So you can pause and look at these if you want. Next slide. And this one is so trivial that I'm just going to go ahead and let you do it on your own, but I'll give you a hint. If the L number is 0, what kind of a suborbital would that represent? So remember, we've written this several times. We've said S, P, D, and F. And then for each of those letters, we've associated a number. And also a shape, right? So for example, you may remember that when we talked about S, the S suborbital, we associated a number with that. And then we also talked about a shape that was associated with that. So I'll let you take that and work with that. Try to remember what the shape was for that L equals 0 subshell, and then only one of those answer choices matches that. And then you can pause this on the next slide and look at the answer. And I'm going to go ahead and keep going. All of the orbitals, and I'm reading the top part of 15, in a given electron shell have the same value of what? So look at your answers here. It's going to turn out to be answer choice B, the same principal quantum number. We'll have everything in a given shell, main energy level, has the same value for N. The N, our principal quantum number. So the N quantum number is also called the principal quantum number. So if it's N equals 1, then everything in that shell will be N equals 1. N equals 2 is the same thing. N equals 3 is the same thing. We only use up to 7 in our class because there are only 7 periods on the chart. The second part says all the orbitals in a given subshell. So this is going to be like your L number, like your S, P, D, or F. Okay, so those are going to also have the same principal number. If they're in the same principal shell, then they're going to have the same principal number, but they're also going to have the same angular momentum, or L number, because they're in the same subshell. So the answer is going to be, it's A is true. That's the L number will be the same, and also the N number will be the same. So the answer is going to be F. And again, I'll let you pause the next slide if you want. Next slide. And then let's go on to the next one. Which electronic configuration denotes an atom in its ground state? So let's go through these one at a time. This one is just wrong. You can't have 2 ups in the same shell or subshell. Here, this one is wrong because Hund's rule is violated. So for this to be correct, you would have to have an up arrow there, and this one wouldn't be here. So this one would have to be moved over to the next available spot, and it would have to be spin up. So that answer choice B is violating Hund's rule. This one would not be in a ground state. It's possible that it could be like this, although it would more likely be like that. If it were in an excited state, because that means excited state means some of the electrons have been bumped up. But it's not asking for excited state, it's asking for the ground state. So that is not going to work. So C won't work, B won't work, and A is just plain wrong, as the man said. It's just plain wrong. So what about D? Well, we've got up, down for 1s, up, down for 2s, so that's okay. And then we've got up here, and then, we've got up here, and the way we've been doing it is we usually would put the second one right there just because it's logical to or just sequential, but it's okay to put it over here. So actually this one does work. That does work. E doesn't work because you have an electron that should be right there down that's been bumped over here to the 2s. So this is another excited state. So E is kaput. So the only one that's even left to consider would be D, and it turns out that's the right answer. And so we're at 45 minutes, so let's wrap it up. So here's the answer to that down at the bottom here. So let's go to the next one, which I believe is the last one. All right. Francium is a radioactive element. And remember, we looked at this before. It's at the very bottom left in the first column. Okay. So what the electronic configuration would be here would be if it lost its valence electron. So remember here for part A, let me finish reading the question. So it's a radioactive element found in some uranium minerals. It isn't uranium. It's just that it's found in with, they should probably have said in with some uranium minerals, and it's formed as a result of the decay of actinium. So for part A, it's very easy. It's just going to be francium plus 1. Which means that it's going to have the same configuration as radon. So remember we said before that francium would have the configuration of radon plus one more electron, which is its valence electron, which was in what row? 7. So 7s1 was its actual configuration. So that's its atomic configuration, but it's not asking for that. It's asking for the most common ion, and the most common ion would be if it gave up this electron right here, which is in the 7th row. And it would tend to do that in reactions because that would give it an octet. So if it did that, it would have the configuration of just the radon without that. So it would just be this part right here. Now let's go to the harder part, B. It has been estimated that at one time there's only 1 ounce of francium. So how many atoms of francium would be there? So you do this in 2 steps. For B, you first of all have to use your conversion factor to go from ounces to grams. So whatever it is, you multiply 1 ounce times your conversion factor, which it takes forever to do this. But anyway, so you want your conversion factor to be written so that ounces are on the bottom, which I'm guessing it's going to be, and I'm not sure about this because I don't do this much, but I'm guessing it's going to be like 1 ounce equals a certain number of grams. Anyway, whatever it is, so I'm going to put question mark on the top. Grams. Ounces are going to cancel, and you're going to get an answer in grams. So let's just put equals question mark grams. But you really don't want it in grams either, because what you're going to have to do is change it to AMU. So let's put question mark grams. And I'm not going to write out this next conversion, but it would be whatever number of grams you got here, multiply that by how many AMUs are in 1 gram. Or if you want, you can put like, you're going to have an answer to the first step in grams, and then you can put that the fraction 1 gram on the bottom, and then 1.66 times, or actually it would be 1.66 times 10 to the minus 24th grams in 1 atomic mass unit. So put atomic mass units on top. And the reason is because you want to get this into atomic mass units. And then what you want to do is you want to divide that by whatever the mass of francium is, which, I mean, here's one of the ones that they have available here. So anyway, find out how many atomic mass units are in 1 ounce of francium. So it's a 2-step process. First, convert ounces to grams. And then secondly, take the number of grams that 1 ounce equals and then convert that to atomic mass units. And then you want to look at the chart and find the chart's mass for francium, which I'm not sure if it's 223 or not. I'd have to actually look at it. So anyway, divide the number of AMUs that you got in your first 2 steps by 223 or whatever it is, and that's going to tell you how many atoms there are of francium. And then let's finish the problem. The longest lived isotope of francium is 223 francium. What is the total mass in grams of the neutrons in 1 atom? So you do this one in reverse. So first of all, if it's 223 francium, you're going to have to find the atomic number for francium, which I'm off the top of my head, I'm remembering the number 85 or 87 or something like that, but I'm not sure about that. But anyway, let's just take the case that it is 85, and unfortunately I don't have a chart available because I'm actually in a different room than I ordinarily would work in. For various reasons that have to do with making these videos, I have to get in a quiet place. So anyway, so the way that you would get the number of neutrons in one atom of francium would be to subtract from 223. Now 223 is going to be the total number of nucleons in an atom of francium. So in other words, it's going to be the proton number plus the neutron number, but they're asking us to find something that has to do with neutrons, so we need to get the number of neutrons. So that means we need to subtract 223 minus the number of protons. So just on a chart, just find francium, find its atomic number, which again, as I said, I think it's 85 or 87, and so whatever it is, subtract that from 223. And what's that going to give you? It's going to give you the number of neutrons in one atom of that isotope. Now, when you get that number, like let's just assume it's 85, so that's 218, and then minus what? 80 would be 148, I think. So 148 neutrons. I'm not going to write it down because I'm not sure if it's right. But let's just round it off and say that it's about 150 neutrons in one atom of francium. Then those 150 neutrons, we're just going to say, would weigh approximately 150 atomic mass units. Just 150, 150. Just assume that one neutron weighs 150 atomic mass units. Which we already said that that's not exactly right, because we said that the atomic mass unit is kind of like an average mass between a neutron and a proton, but just for the sake of argument, just leave it like that. And then just convert back to grams. That's all you have to do. So you just go in the reverse direction for what we did in part B. So you multiply by your conversion factor, but you flip the conversion factor because you want now the grams to be on top. So write, for example, 1.66 E minus 24 grams on top, draw a line, and on bottom put 1 AMU, and then multiply it by how many neutrons you have. Let's go ahead and look at the answers here. So the answer to part 1 is just radon. That's the shorthand form, so that's the easiest way to do it. For part 2, here's the conversion factor. It's actually about 28.35 grams makes 1 ounce. So when you convert this, you want to convert ounces to grams, so it would just be 28.3495 grams. And then when you convert 223 AMUs, which that was the mass of the francium, times your conversion factor, which you want the AMUs here to be on the bottom and the grams on the top because you want to get it in grams. Okay, so I actually did this one differently. So anyway, you can do it either way. You can do it the way I said before. You can do it this way. So if you convert this to grams, 223, actually I did it the other way, but 223 AMUs, actually it turns out to be the same thing. So 223 AMUs will convert to 3.7 times 10 to the minus 22nd grams. And then you know that you have a total of 28.3495 grams. So divide that number by the number of grams that one atom weighs. So it's actually the same thing. You get that you are going to have 7.658 times 10 to the 22nd atoms. Then for part C, we're coming up on an hour, so I'm going to have to finish this. And it turned out that the number was 223, and the number for francium for its atomic number was 87. So one of the two things that I said was right. So when you subtract 223 minus 87, you get 136 neutrons. So just multiply that by the mass of one atomic mass unit. Even though that's actually not exactly right, but it's going to be what we're going to have to use. Or, I mean, if you wanted to, well, never mind. So we said that one atomic mass unit weighs 1.66 times 10 to the minus 24th grams, so just use that. That's actually for one atomic mass unit, but anyway. And then multiply that by how many atomic mass units you have here, which is going to be 136. because for the purposes of this problem, we're assuming that one neutron weighs 1 AMU. So multiply 136 neutrons, which you got here, times 1.66 times 10 to the minus 24th, and you get 2.25768 times 10 to the minus 22nd grams, which we rounded to 2.2577 times 10 to the minus 22nd grams, and that's it. So that finishes the chapter up. There's nothing in this chapter that's particularly difficult at all. I mean, really, if you could just remember those two equations, so it's C equals lambda nu and E equals H nu, where the H is Planck's constant, which you can look up in your chart, your formula chart. There's nothing difficult at all about this. Now, I don't think we did a problem in the work problems where we did the Balmer-Rydberg equation, so you may want to go back to the lecture notes, even if you didn't have time to go through all of the lecture notes. You may at least want to go back to the part that talks about the Balmer-Rydberg equation, where you end up multiplying this Rydberg constant times 1 over m squared minus 1 over n squared, which I'll just briefly write that out here, where m is what you're falling to. So if you're falling from 3 to 2, then you would put 1 over 2 squared, where the 2 is what you're falling down to, minus 1 over 3 squared. All right. So here would be if you're falling from n equals 3 to n equals 2. This is what you would write. So you just figure out what that is. So it's going to be 1 over 4 minus 1 over 9. So do that on your calculator. 1 over 4 minus 1 over 9. So 0.25 minus 0.11. And then multiply it by this 0.011 nanometers to the minus 1. And then take the reciprocal of whatever you get, and that's going to be the wavelength. That's called the Balmer-Rydberg equation. And we didn't do one of those in the work problems here. It probably would have been a good idea for me to put one in, but at this point it's too late, obviously. So if you want, you can go back to the lecture notes, because we actually did one or two problems in the lecture notes where we used that formula, or go online and just ask for a sample problem using the Balmer-Rydberg equation. And having said that, let's stop, because we're actually coming up on an hour. I didn't think these were going to take that long at all, but I guess that's okay as long as we get through everything. So let's stop, and that's the end of chapter 6, and I'll see you in chapter 7.